Okay, 28. Let's not do this again. But the important notion is 28 is fewer than 40. So we will stay in the regular lecture hall. I was expecting this to happen. That always happens. 60 sign up, 40 show up, 20 do the exam. This year we had 90 sign up, and anyway, it always works out. Where are we? Here, right? This is us. We have an exercise on Thursday, which means homework. And the homework is problem 6. And problem 6 basically tells you to go through 2 example scripts that visualize single transformations and double transformations. So all we're going to do is draw coordinate systems on a screen, and you get a bunch of object-oriented MATLAB code that draws coordinate systems onto the screen. And you should understand how that works. It's not, I don't think this is going to take a lot of time. Just have a look at these 2 files, and then the final question is extend this to include a 3rd rotation, which is not of high difficulty, but it's sort of a nice check. Okay, did I understand how this framework, how the visualization works? The biggest challenge here is that you need to set up Git. Who has not set up Git yet? Or let's turn it around. Who has set up Git? If you don't have Git running on your computer, you cannot do the homework, you cannot participate in the exercises, right? This worked in the first exercise where everything was based on tutorial from MATLAB, but now you need the framework that we give to you, the framework that visualizes, in this case, coordinate systems, and in order to get that framework, you have to get Git running. The information you will find if you click here on MATLAB. It will give you 2 videos, one video that talks about what Git is. It doesn't go into the details, but it's 2 parts. I think the first part is sort of in general, what is Git? You can skip that if you know that already. And then the second part is how do we use Git in this class, right? Where do we upload, or where do we push things? From where should you pull? And how does that work with solutions and templates? This seems to be a lot of work, just to get a couple of exercises. And people always figure out alternative ways of doing this, going through the GitHub webpage that comes with the class, and then just download a zip file and keep downloading a zip file every 2 weeks. I highly recommend that you invest the time, because it's a super important skill to know how to use Git. Every company, I would say virtually every company today, uses Git to manage their code repositories. So an extremely useful skill. Has nothing to do with dynamics, but we take it as a means to force you to do this. Until today, and then I should say problem 7 and 8 are then reasoning about velocities. So rotations of coordinate systems, rotations of rigid bodies, and derivatives in moving coordinate system. It's going to be a lot of fun. Until today, we had these 2 more theoretical homework sets. There's 2 seats down here. Actually, can we do a little exercise? This happens every year, that benches move forward. And can the back row move back by about that much? Is that possible? And then you don't have to do that much, so you still need to get out. But we're really talking about 10 centimeters here. If you get 10 more centimeters, you can breathe again. And then there's 2 more people who can fit in here. Actually, other way. Breathe in. Good. I wanted to start with a quick look at these 2 problems. We call them problem 18 and problem 13, which were homework for today. And I'm not going to give you the actual solution, but I want to talk a little bit about structure here and physical intuition. Problem 18, this is what I want to start with, basically says, hey, you have a point, point B, and that point B doesn't talk about velocity, but let's assume it is stationary, at least at the moment, because that point B has a given acceleration AB, which the whole problem is planar, has an AX and AY component. And then this body is rotating about the 3-axis with a angular rate omega, and that angular rate changes with some omega dot angular acceleration. And the question now is to find a point, and then a point Q is given. I should finish that first through some vector RBQ, which again is a planar vector. And the problem is now to find values for omega and omega dot that this point Q here is not accelerated. So we're basically looking at, where is it? Oh. At this equation, right, where we have B given, RBQ given, AQ should be 0, and we're looking for these 2 values here. So just applying that equation. What this basically means is, we just saw it in the equation, that in this point Q, I somehow have ABQ, right? The translation is applied to the entire body. But at this point, I need to find a compensating acceleration that comes from this omega squared plus omega dot, right? And if you go through this problem, fairly simple, right? You just use the equation that I showed you. You solve it for omega and omega dot, and you get something that looks like this. Omega is plus minus the square root of something, and omega dot is some fraction. Who got these results? Where do they come from, right? Without going into the details, but why do I get the square term for omega? And what does that imply, right? And it has this plus minus notion. So it doesn't, obviously it doesn't matter in which direction I rotate. And square root always can have issues, right? If the expression under the square root becomes negative, and then I would all of a sudden get complex angular velocities, which tend to be tricky to implement in real life. So the question is, where does that come from? That structure of the solution. And what I basically want to show you is that in this point Q, I somehow have to compensate for this acceleration AB through rotation and angular velocities, and somehow generate an acceleration that is equal, right, through these rotations, generate an acceleration that is equal to the red arrow. And if I assume that the point B is momentarily stationary, it will not stay stationary forever because I have an acceleration AB. But if I assume just at this very moment it's stationary, the point Q is moving in an arc around point B. The angular velocity, the velocity tangential to this arc is given by omega times this lever arm. And then what does omega dot times this lever arm give me? An acceleration, right? So omega dot times the lever arm from here to here will give me an acceleration of this point Q, which is going to be somehow tangential to this arc. And if my omega dot, right, so omega determines the velocity along this arc, omega dot determines how that velocity changes, how, in a sense, the speed on that arc changes. So an omega dot will somehow give me a green arrow. And I can make that green arrow point to the left. If I increase omega dot, I can make it point to the right if I decrease omega dot. So this is why I don't have any problems here. How does omega influence the acceleration that this point sees? Right? It is moving, at least momentarily, on an arc or in a circle around this point B. So it sees a centripetal acceleration. Right? Without acceleration, the point would move in a straight line, but it's moving on a circle. So it has to be continuously accelerated towards point B, which is this expression here. This is a centripetal acceleration. And that depends on the square of the angular velocity. And because of that, the angular velocity has the square root expression. It also doesn't matter whether I go counterclockwise or clockwise around the circle. This acceleration component will always point towards B. That explains the plus and minus sign, right? It doesn't matter whether I go clockwise or counterclockwise. Now, what would happen physically if the term under the square root becomes negative? Where would this problem fail? There's a seed. Right? Why would I get a negative term under the square root, which would result in a complex velocity omega, which I cannot realize physically? When does that happen? Right, just to summarize, this point B sees AB. This point Q sees AB, and in addition, an acceleration that comes from the rotation and rotational acceleration. The rotational acceleration gives me something tangential to the arc. The angular velocity gives me something that points towards B. And then the sum of green and blue, if they equal red, right, and I scale them, can scale them by changing the magnitude of omega and omega dot. I can scale them that their sum equals the red arrow. And then if black and red are the same, this point Q will be not accelerated. But when does it fail?
If AB has a negative y component.
So if AB, if I give you as a problem an AB, let's call it AB2, that points down, what would happen then? You would need a blue acceleration in this direction, right? Because I would somehow have to compensate now for this acceleration, which I can do with the green arrow, but then I would need a blue arrow that points up, and that's never possible, right? The centripetal acceleration always points from Q to B, no matter in which direction I rotate. So if my acceleration here is pointing in a sense downwards, right? You said negative y direction. If we add a coordinate system, then the term under the square root would become negative, and no solution exists. Okay, just to show you the structure here. And then I want to move to this other problem, problem 13. Well, yes, Julius, yes.
Problem 18.
Yeah.
So in the exercise, it stated that the point Q is not accelerating, but in the I coordinate frame, whereas the other the other values were given in the B coordinate frame. So I was wondering how you can transform that the acceleration of the point Q in the I coordinate frame is 0, how you can transform that into B coordinate.
Okay, good question. Probably just a typo. So I have to look into this. But the answer is, if your acceleration in the I coordinate frame is 0, how large is your acceleration in the B coordinate frame? It's also 0, right? And this is where we have to be, again, careful, because I think in the back of your mind you think, wait, this coordinate system is moving, so the acceleration should be different. But as soon as I write A, I mean physical acceleration. And physical acceleration means relative to our frame of reference. Not to a coordinate system, but to this frame of reference relative to the world, right? And if that is 0 in one coordinate system, it's going to be 0 in any other coordinate system as well, right? Only if I give you a value, then you would have to do, of course, a transformation. But all you would do is a simple transformation, no transport theorem or anything, right? If A is given in I and I want A in B, then I do small a, acceleration in I. I want it in B, then I just do capital A, B, I as a transformation matrix, and that's it, right? So that's the point, right? This is why these derivatives are tricky, because you always think, oh, in one system it's not accelerated, in the other system it is accelerated. No. As soon as I talk about physics, I always mean in this absolute frame of reference that we call this room, and that is true without any coordinate system and is true in any coordinate system. Okay, but good point. And can you do me a favor and send me a quick email? Because in 90 minutes I will have forgotten about this and I need to tell someone to fix that typo. Maybe it was intentional. Who knows? Any other questions? Problem 18. Sorry, I'm going a bit too fast maybe. Then problem 13. And here we're looking for the twist axis. So I was trying to find a point t, given through some vector rbt, that the velocity of that point t is parallel to omega b. And all of these are assumed to be body fixed points. In other words, I'm trying to find the twist axis. It's something I think we do in exercise 3. Where we then try to visualize a twist axis. So this is actually something that everyone needs to do at some point to be able to do the exercises. If you approach this naively, you say, well, easy enough, right? I know that these two vectors have to be parallel. So I simply say that the velocity of point t is in the cross product of omega b is equal to 0. Easy enough? That means the cross product of omega. And now I say, OK, this is a point on a rigid body. So I can basically go ahead and plug in this equation. So for Vt, I get Vb in b coordinates in this case, plus omega b in b coordinates times this vector rbt. B coordinates still equals 0. And then I can rewrite that. So I identify on the left-hand side, I have now omega squared times rbt, which is my unknown. And everything else I threw to the right-hand side. VB, B, because those are the known quantities. And then I do what? Oops, don't do that. What do I next? Right, I want to solve for RBT. I multiply from the left with omega b squared inverse, right? And then I have it. Then I get RBT equals some expression, everything is known. Did anyone try this at home? What's your recommendation? It doesn't work because the inverse doesn't exist. Don't try this at home, right? Exactly, the inverse doesn't exist, right? This is a skew-symmetric matrix. We talked about this. It represents a cross product. Cross product represents a projection, and projection means multiple vectors are mapped onto a single vector, so it's not something that you can invert. So that, of course, also means you cannot invert this omega square. Physically, that's because this problem, the way I've wrote it down, is ill-posed. There's not one single point t that fulfills this condition, but the entire twist axis, every single point on that physical line would fulfill these conditions, because every single point on that line, that's basically its definition, is only translating in the direction of of omega b, right? So that holds for any point on this axis, and this is why I'm asking here for find a point and not find d point. So we need additional information, right? If you want to solve this mathematically, you have to throw in another constraint that basically says, out of all these points on the twist axis, right? Here's B. This is your point B. You know that this is the twist axis. I could pick any of these, and I should pick one, right? How you do this doesn't really matter, right? A common approach in these cases is to say, I want the closest one, which means basically that this vector rbt, right? So this would then be my point t. This vector rbt is perpendicular to this direction here, which is my omega b axis. And that would then give you an additional condition that you should need to somehow get into these equations. And then there's different ways of doing this. You could, for example, try to figure out what the direction of RBT is, because RBT is orthogonal to this line and orthogonal to the velocity at point VB, and then you introduce some scaling value and solve for that scaling value. You could use the triple product formula. How's this called in German? I always have to look this up. You learn this in Technische Dynamik as the Grassmann-Identität. Grassmann identity, triple product formula, double product, triple product, because it's three terms, right? You have two cross products, three terms. You can turn two cross products into the sum of two dot products. So you can look that up and then somehow get sort of this notion into one of the dot products. Or what did you do?
I projected VB onto omega B, and then I had a parallel component and could calculate an orthogonal component.
Okay.
And then via the cross product, I could calculate RBT.
Okay. What did you do after you figured it out?
I stopped.
You stopped? Did anyone have a third solution apart from the two that I mentioned? So what you did sounded a little bit like sort of like the first solution. You figure out the direction and then scale it. You could do a pseudo-inverse, right? If this fails, mathematicians don't do this, but engineers, once this fails, the next thing they do is they do a pseudo-inverse. Because, oh, OK, there's no solution, then let's take the next best thing. In this case, the pseudo-inverse will give you the vector that is shortest, which, at least if you understand what's happening in the background, is exactly what you want. Right? So if you do the pseudo-inverse, you get the shortest vector RBT, right? Of all the possible candidates, right? Every other vector is longer, and the pseudo-inverse will give you the shortest, so that can work as well. Good. Questions? Questions on problem 13? Any other approaches that you tried that worked, did not work?
Build a linear system that didn't have to visualize the matrix.
And you still can solve it, right? Because it's underdetermined, yeah. But you could, in your linear system, you could throw in something like this, where you say there's now a few more equations that say this vector and this vector are orthogonal through some dot product being equal to 0. And then you could solve it. OK, I then want to show you this again. So now we are talking dynamics. We're trying to get the relationship between accelerations and forces. And we're doing this for systems of particles, which at this point are just point masses floating through space, not connected to anything. And in the last lecture, we didn't do anything really smart. Right? All we said was for each of these points, Newton's second law has to hold. And then we get a bunch of equations that look like this. And we sum up over all of these. And then we said, OK, we also want something for rotations. And we basically took these equations and pre-multiplied them in the sense of a cross product with some vector from a reference point to my point mass. That's what we did here. And then we also summed over all of them, right? And if I have two equations and then I sum over all these equations, of course, the sum on the left and the sum on the right should be equal. And to make this look fancy, we ultimately introduced a bunch of abbreviations where the sum of all moments is ma, or sum of all torques we call ma. This sum we call dA, the kinetic moment. This sum here we call the vector to the center of gravity. And the sum of all these guys here, of these, we call overall P. And the sum of this we call F. And then if you do this, you get really beautiful equations that look deep because they're short and they have big symbols. And we haven't really won anything. Because as soon as I plug this back in, I'm just back to the sum of Newton's second laws for each single particle. With one exception, we realized that everything that we consider to be in the same system has interaction forces, internal forces, and those, according to Newton's third law, have to come up in pairs. Right? There's one force acting from body A to body B, or point A to point B, and another force from B to A. And those are equal and opposite in sign, equal in magnitude, opposite in sign. So if I sum them up, they cancel each other, and I get 0. And the same holds for their rotational contribution, the torque that they produce. That's a little bit harder to see, but ultimately you can move them along their line of action. So I can move this line to that point, and that that force to this point, and that force to the other point. And in this process, the torque doesn't change. And through that, I can then also align the lever arms, right? Because here, we still have this cross product with these lever arms. So it's not immediately obvious. I skipped over the details, but this is 0 as well. What can I do with this? So far, not a lot, right? I mean, we have a notion what the resulting force F is. We maybe have a notion what the resulting force ma is. For translational motions, we kind of know what the acceleration of the center of gravity is. And if I have a rigid body, we kind of know that the center of gravity will be a body fixed point. So for a rigid body, this may be helpful. This is not, because here accelerations show up, and they show up in a cross product, and the cross product cannot be inverted. So if I'm trying to get from the moment here, the torque ma, to my accelerations, I cannot do it because I would have to invert this cross product, right? And that, of course, is physically not possible, because if these points are not connected in the sense of a rigid body, they could move in all different ways, and there's no way of predicting this. So at this point, what we can do is we can, let's see if this works. I don't have internet. We can look at something like this. So this is truly a system of particles. Little water droplets connected through the pressure that is created by this balloon. And if you look at this, I can say, OK, sum of all forces is the overall force. The only forces acting here are gravity. Overall force is mass times g, pointing downwards. Center of gravity somewhere here in the middle. and this would basically check out, right? If I track a position of the point here in the middle, it will be accelerated with f times g. But this still holds right now, right? Now we have all this internal movement, and we kind of can guess where the center of gravity is. I'm trying to point there, and the center of gravity is still following sort of this rule, right? Accelerated downwards. But of course, yeah, this is how far I pre-downloaded the video. Of course, that doesn't help us if I'm interested in the individual accelerations of these particles, right? I need to know what's happening in between in terms of these blue forces, or I need to know some kinematic constraints, which I get as soon as I assume this is a rigid body, not a water balloon anymore, but rigid body. Then I know they all have to follow an acceleration, and that acceleration is basically determined by these rigid body equations. I want to now take a detour and introduce a different quantity that is slightly differently defined than the kinetic moment, right? We had the kinetic moment being here, the sum over mass times lever arm cross acceleration. And now I'm introducing something that is sum over mass times lever arm cross velocity. And we will call this the angular momentum, abbreviated L with a reference point A. So these vectors here are AI. They always start, and those should be vectors. Pardon this. That should be a vector, of course. That vector starts at point A and goes to each individual particle. And then I get sort of individual contributions to the angular momentum. And then I get, as the sum, I get the total angular momentum about a point A. Quick note on language. In German, this is called Drall. And if you took your mechanics lecture here, you said Drall only exists if A is stationary. Here, I want to relax this. I allow A to move. We'll see in a second what that means. In English, there's different names for this. Number one is angular momentum, compared to the linear momentum. That would be sort of linear velocity times mass. Linear momentum is sometimes called impulse, so impulse, linear momentum, and then it's also sometimes just called momentum, right? So if you talk about the point mass, it can have an impulse, it can have a linear momentum, it can have a momentum, all the same thing. Here, we can either call this angular momentum, or sometimes this is called the moment of momentum, where in English we kind of use this concept that in German you would say, ich habe ein Moment, ein Drehmoment, ein Moment, is always applied sort of the moment of a force, so a torque. Here we can also have a moment of something else. And this is basically the moment of momentum, because m times v would be momentum, linear momentum, impulse. And then I take a moment by multiplying this in the sense of a cross product. So whenever you have a cross product, you get a moment of momentum, more commonly known as angular momentum. This is how I will call it. And then you have to be very careful not to confuse moment and momentum, where moment would be if it's a moment of a force, and if you don't specify what moment it is, normally it means moment of a force is equal to a torque. So those are again synonyms. And then momentum is impulse. And that can be a little bit confusing. This is why I try to make a quick note here. This is how this guy is defined. And in contrast to the kinetic moment that we saw on the previous page, the advantage here is I can always compute this, because in a dynamic system, no matter whether I do forward or inverse dynamics, I know what velocities are. Right? I'm trying to get a relationship between forces and accelerations, and that means I know what velocities and positions are. So this is something that I can always compute. I can change the reference point. So if I want to go from point A to point B, this is the equation here. Basically, what I do is I write this vector RBI as the sum of RBA plus RAI. And then here I get the sum over all the impulses of all the individual linear momenta of my particles. And that sum, we defined that before as the total linear momentum, p without an index. And then what we see back here, of course, this is the angular momentum about our point A. And this is here my transformation rule. LB is RBA cross P, total momentum plus L about A. Now, for a rigid body, with the center of gravity as a reference point, right? So I'm now computing LG. I can basically plug in for the velocity now this equation for velocities on a rigid body. So instead of Vi, I say this is Vg plus omega b cross Rgi, right? So Vg is my, or G is my reference point, and this gives me the velocity of an arbitrary point I. And I can now take this apart, and then the first term I would get is basically sum over all mi's times Rgi cross product with Vg. And so the question is, what is this? Sum over all masses of individual particles times the vector Rgi, vector to this particle. What will this give me? If I sum over mass times position, what do I get? You look so knowledgeable. So I get the vector to the center of mass. Right? And the center of mass would basically take that sum and divide it by m. So I have to multiply that with the total mass, m. But where does that vector start? Right? It gives me the vector to the center of mass. Where does it start? Well, it starts where all these Rgi's start, right? And they all start at G. So that gives me the vector from the center of mass to the center of mass. Turns out that one is rather short. So this part here doesn't contribute. This is all 0. And in the back here, I can rewrite that. First of all, I can write my cross products with this tilde notation. And then I can also flip the order of the mi and sort of on purpose pull the omega b, which also should be a vector, sorry about that, to the right. And now I'm missing one thing. Right, so I just rewrote the cross products with tilde operators. I flipped these two. And then, it doesn't matter in which order I evaluate these. These are now all matrix multiplications. So I specify that I do this one last. But what's missing? This little guy, right? I still need a minus sign. I could do this by adding a minus sign somewhere here. I do this by adding a transpose, because these are skew-symmetric matrices. So a transpose of this matrix is equal to its negative. So this is me just adding a minus sign. And then I can, sorry, this is a little bit too much because I didn't talk about the sum yet. But since omega b doesn't depend on the location I, right? This omega is the angular velocity, which is the same at every point in the body, right? It's one quantity for the entire rotating body. I can pull the sum or pull it out of the sum, and I basically get this thing here, which of course has to use masses mi. And I get 3 by 3 matrix times 3 by 3 matrix times a scalar. So I get a 3 by 3 matrix, which we call the inertia matrix. So this is Ig, the inertia matrix. And this allows me now to get a very, very compact formulation for the angular momentum. The angular momentum of a rigid body is the inertia matrix multiplied with the vector of angular velocity. Here I've written in b coordinates, where this is a matrix. If I write this coordinate free, I should more correctly call this an inertia tensor, right? Because it doesn't live in a coordinate system yet, but here we write this down in coordinates. So now this is a matrix, and this is how this matrix is defined. If you evaluate this, you go through sort of this building this skew-symmetric matrix, building this skew-symmetric matrix, multiplying them, sort of saying my vector RGI has the components rho 1, rho 2, rho 3, you got this. And this being a repetition, I'm sure everyone has seen these inertia matrices. What's the benefit? If I express this in body fixed coordinates, these vectors are constant, right? G is a body fixed point, I is a body fixed point, meaning this vector has a constant representation in a body fixed coordinate system. I have to figure this out once. I do the sum, and this will never change, right? So in body fixed coordinates, Ig is a constant quantity. And that is super useful. You compute it once, and then your body rotates. And of course, in space, right? If I have inertia properties and the body rotates, the absolute inertia properties change. If I go from this, right, my mass is oriented this way to this, my mass now is oriented this way. So the inertial properties of a body change in our frame of reference, right, in absolute terms. But if I express them in a body fixed coordinate system, they're always the same, right? This is why we use body fixed coordinate systems. And I hope you've seen all this. That's why I went through the derivation a little bit quicker. What I want to do now is I want to give you some intuition about what this L means, where it comes from, and what these individual terms mean, right? Why do I have the sum of squares on the diagonal? Why do I have the minus sign and these products on the off diagonal? By the way, these are called the moments of inertia, and these are called the products of inertia. We all saw this in exercise 1 in SimScape multi-body. They don't ask for a 3 by 3 matrix, but they ask for 6 values, the 3 on the diagonal, and then the 3 here, and you all know they are symmetrical, so I only need to specify 6 values for this matrix. What I want to do is I want to add a little bit of intuition where what angular momentum means, what this matrix actually does in the background, why it has the structure, and then you all know this property that because this is a matrix, the vector of angular velocity and the vector of angular momentum are not necessarily collinear, right? They can point in different directions. You can rotate around this axis, but your angular momentum points in that axis. And I want to talk about why that is the case. And we will do this with a super simple example. So what we will do is we will look at a single particle. Single particle. And sort of the special case of omega b being a rotation purely about the one axis, so small omega 0, 0. That is very general in a sense, because I can always rotate my coordinate system to make that true. And then lastly, the velocity of our center of mass should be equal to 0. in this case, right, my angular momentum about g would be the product in some b coordinates, would be the product of my inertia matrix with this vector omega b. And that would simply give me the first column of the inertia matrix, right? Because I multiply with omega 0, 0. So I get the first column of the inertia matrix scaled with small omega. And that would then basically be the sum over all n. And then we had omega 2 squared, omega plus omega 3 squared. We had minus omega 1, omega 3, and minus omega, omega 1, omega 2. And this is minus omega 1, omega 2. And that gets scaled with omega. And it should be a transpose because it's a column vector, right? This is sort of the result that we should get. I'm missing something. What did I miss? Mi. Right? It has to be scaled by mi. So somehow the angular momentum will have this form, and I'm trying to figure out where is that coming from. And I want to do this graphically. So let's draw a little coordinate system, which I orient in a way that we look along the one-axis. So 2 points up, 3 to the left. That is a nice right-handed coordinate system. And that means our vector of angular velocity is parallel to the one-axis. So we look straight at it, rotating counterclockwise here with small omega. In this view, I get my particle I with mass mi somewhere here. And its location would be given by the coordinates rho 2 and rho 3. Now, if I want to talk about angular momentum, right, what's the angular momentum of this point relative to my center of gravity, which I have here assumed to be at the origin of my coordinate system? I want the angular momentum that this particle has with respect to g. I want the angular momentum means I want the moment of momentum, which means I first need to compute the momentum of this particle, the impulse or the linear momentum. And to get that, I need the velocity. Who can tell me the velocity of this point? Where is it moving? Sorry, can you say it again? Sorry. Tangential, right? So I draw a line connecting g with I, and then you're basically moving this way. And the magnitude of that velocity, right? If I don't care about its direction, but if I care about the magnitude, how large is that? In terms, I can do a cross product, but here I already work in projections. So it's simply going to be this distance d times omega. So this is d times omega. So that's my velocity. This would be the vector of my linear momentum. P, and let me call this P1 because we're now basically looking at this in a projection, looking along the one axis. And P1, that's simple, right? That is mi times this velocity vi. How large now is the angular momentum about the center of gravity of this particle I about the one-axis. So the angular momentum in the one-axis, which is basically either you can say the first component of the angular momentum, so basically this guy. Here I'm thinking about this in terms of projections. Well, now I have to compute the moment of momentum. So I have to take this guy here and multiply it with, in the sense of a cross product, with this lever arm. But since everything is planar in this projection, and I'm only interested in the contribution about the one-axis, I have here a 90-degree angle, I could simply say that this is P1 times this distance d. And I hope everyone sees this, right? So I basically have now a process where I look at the rotation. Through this lever arm d, I get a velocity. The velocity gets scaled by mass to give me momentum. And the momentum gets again multiplied with this distance d to give me the angular momentum about this one axis. And now it's just a matter of plugging things in. So P is mi times the velocity, where the velocity was d times omega. And that gets then multiplied with d to go from the linear momentum to the angular momentum. And then I get this expression d squared. And d squared is equal to what? So just geometrically, how can I write d squared? Rho 2 squared plus rho 3 squared. And voila, we have exactly this term here, right? Of course, not in the sum, but just for one particle. Rho 2 plus rho 3 squared times rho 2 squared plus rho 3 squared, sorry, to be precise, times omega times mi. And we now see why, if I look at the first element of my inertia matrix, right, I have this expression rho 2 square plus rho 3 square, which is basically the distance from a point to the rotation axis, in this case the one axis, right? And then the second element on the diagonal would be rho 1 square plus rho 3 square, and so on, right? And these are basically distances to your rotation axis, and they have to be squared because they come in two functions. They take the rotational motion, the angular velocity, convert it into a linear velocity v, and then they take the resulting momentum and convert it into an angular momentum. And in both cases, the lever arm is the same, because the axis that generates the rotation and the axis about which we get the angular momentum are the same. Now, next thing, I am interested in the second component. So LGI2, the second component of this angular momentum. And to get that, it makes sense to change our perspective and get a new view where we look along the two axes. If we look along the two axes, I would like my one axis to point upwards. And this is the axis about which we rotate. And then if one is up, I look along 3 points to the right. And this would be the 2 axis. Center of gravity is still down here, g. The particle that we're looking at would be, let's say, here, right? And part of this we've seen on the other drawing. This is why I took a quick measurement, because that distance and that distance is obviously the same. This distance we haven't seen over here because it's a position out of the plane, right? This would be rho 1. And that's an interesting realization, right? If I look at this, I kind of assumed somehow implicitly everything is planar, but turned out that point A wasn't here. It was actually somewhere up here. Nothing in the drawing changes because we're rotating about this axis. The velocity is kind of still in plane, but up here. And then the resulting angular momentum that we get from this is pointing this way. Now, in this new view, right, view A that we have over here, I see that the point is a little bit above sort of the 2-3 plane, a little bit above. If I now start thinking about velocities, how would I have to draw this velocity vector in this view? Where is it pointing to? Into the plane? And? To the right. Right, so we're looking from there. So this is pointing to the right and a little bit down. And I now want to go ahead and give this distance a name, and I call this V2. And it is basically the projection of this velocity into this plane, right? And so I don't see the full velocity. This arrow is shorter than this arrow because I only see this projection. We will see in a second, as soon as I start doing the cross product, why I want that projection. But let's go with this for a moment. So we have V2. We then have the corresponding projection of the momentum or the linear momentum, P2. And sorry, I missed a step. How large is V2? How large is this projection V2? Why rho 2? Right? Why rho 2? So you're right? Of course, it should depend on omega. But why only rho 2? Well, because we're interested in the velocity that way. And that velocity gets larger if we move away this way. If I move from here in the rho 1 direction, all I will get is a velocity down. And no matter how far I go over there, the velocity will be pointing down. So the velocity component downwards depends on the distance rho 3. The velocity component to the left depends on the distance rho 2. And in this projection, what we see is simply that this velocity is rho 2 times omega. And then, of course, P2 is mass mi times rho 2 times omega. Just the projection. Why am I interested in the projection? Because the next thing I'm interested in is what is the angular momentum that this is creating about the 2-axis. And if I just care about the 2-axis, I have to look at this as a projection. Right? Any component into the plane will create angular momentum about the 1-axis, which we looked at here, may even create angular momentum about the 3-axis, which we would have to look in a different drawing. But here, I'm just looking at this projection along the 2-axis. And who can tell me what's the contribution of the angular momentum of this guy? Right, now I have to multiply it with a lever arm. And that lever arm is rho 1. Small detail missing. Minus sign. Because this is pointing to the right, it would basically give me an angular momentum around this axis, which is pointing in the -2 axis. So the +2 axis is coming out of the plane, out of the screen. This is going into the screen. So what I will get here is a angular momentum that is going to be P2, sort of this projection of the linear momentum in the 2 plane, times ρ1, and here with a minus sign. And then I can plug in my numbers again. So I get minus ρ1 times mi times ρ2 times omega. And voila, this is exactly what we have here, right? Minus ρ1, ρ2 times omega times mi. That is the contribution that we get here. And I'm skipping this. Now I could look along the 3 axis. Along the 3 axis, I would see this velocity v3, which would be negative omega times ρ3. And then I would, again, have to multiply it with this distance. And that would give me a third component, or the third component of the angular momentum. What I'm trying to show you, I mean, we're training a little bit spatial representations and thinking about different views and projections and so on. But I also want to explain to you sort of this property. Why is the angular momentum vector not aligned with the angular velocity vector? Because the angular velocity generates a linear velocity. And if the linear velocity if everything is planar, right? This doesn't happen for planar bodies. If everything were planar, this guy would sit down here and would not produce an angular momentum about the 2 or the 3 axis. But because it's somewhere up here, I get sort of this additional lever arm. And the concept behind this is that we're basically thinking about lever arms. We always have one lever arm that creates a linear velocity and one lever arm that creates angular momentum. On the diagonal, those 2 lever arms are the same, and we could call them D, because the lever arm that creates the linear velocity and the lever arm that creates the angular momentum are the same. This is why we get the square term. On the off diagonal, those 2 lever arms are different, right? The velocity is created by omega 2. The larger omega 2, the larger this velocity component. The angular momentum is created, ρ2, right? The angular momentum is created by this lever arm ρ1. So we have 2 different lever arms, one to create the velocity, one to create the angular momentum. And then you have all these other properties of the mass matrix or inertia matrix. Is, for example, what happens if I have a point down here at the symmetric location? Would have the same velocity, would have the same linear momentum, but since it's below, it would have a negative contribution to the angular momentum, which would be equal to the positive contribution here. So in this symmetrical configuration, that angular momentum and that angular momentum would cancel each other. This is why symmetrical bodies typically have a diagonal inertia matrix. And we will see that in some more detail later. Question?
Yeah, I think there's a little typo in the sum there. You wrote ρ1 and ρ.
Thank you. You held back all this time to correct me. Thank you. Or you just see it?
Just a minute before.
Okay.
Other question, if people are jumping to water from 20 meters, so there is like possible. I saw it like they jump like to roll to front and then to the side and stuff like that.
Mm-hmm.
And my question is it because of this, that it's even possible. Okay.
Yeah, because we will see in a second that the angular momentum remains constant. So the angular velocity is kind of disconnected with the angular momentum, and so you can do these tricks. Yeah, yeah, we get to this in just 1 second. Good point. Any other questions? So, a little bit of background. You will get a few videos about the inertia matrix for those who haven't had the background, but I think most of us have seen enough inertia matrices. Again, here the focus, the flavor of the class is on intuition, so I wanted to show you this. Now, we somehow have to close a gap, because here I know total torque versus is equal to kinetic moment, and then I started talking about angular momentum. And so next step is basically to establish the relationship between the angular momentum and the kinetic moment. And I start here by taking simply the time derivative of the angular momentum, right? Angular momentum depends on velocity, kinetic moment depends on acceleration. So I think that's a logical first step, to take the time derivative of your angular momentum. And if I look at the definition, I go ahead and simply apply the product rule, where I say, well, I have to take the derivative on v, on the velocity, and I have to take the derivative on this vector RAI. In theory, I should take a third derivative if I apply the product rule. What would be the third derivative? And why don't I do it? And what's the third factor? Mass. So I should, in theory, write m dot, but we assume that my masses are constant. I then do a little trick here, and I write this vector from point A, reference point A, to I, as the vector from my inertial reference, so sorry, R, I, capital I, small I, minus the vector from the inertial reference to point A. Right? And the difference between these two will give me exactly the vector from capital A to small I in positions. And then, of course, the same holds if I take a derivative. The derivative means that I can write this here, right? This would be the velocity of point I. This is what we see back here. And this is the velocity of point A, which we see back here. So if I pull this apart, I get the sum over velocity of point I cross this minus velocity of point A cross this. That first cross product will evaluate to 0, because vi and mi times vi are parallel, right? So that cross product is always going to be 0. And for the second term, right, so I copy down here, and this, of course, here, should have mentioned this, right? This is mi cross acceleration, physical derivative, mi times acceleration. That is exactly the definition of my kinetic moment. The sum over lever arm cross mi times acceleration is dA. So the time derivative of the angular momentum about point A is the kinetic moment about point A minus VA cross the sum, right? Here I can take the sum back to everything that has an index I. And the sum of these guys, mi times vi, is the momentum of each particle, linear momentum. Sum over all linear momenta is the total momentum p of all the particles together, and the total momentum we can write as m times the velocity of the center of mass. And now this gives me sort of this final equation where I say the derivative of the angular momentum is the kinetic moment, minus VA cross m times VG. Why do I have two terms here? And you may not have seen the second term before, because in our undergrad mechanics classes, we typically assume that A is stationary. And if A is stationary, this is going to be 0, right? It's not going to contribute. So we can immediately see this has something to do with the velocity of point A. Now, if you think about angular momentum, it can change two ways. Number one, the physics change, right? You apply an external torque, and somehow the body accelerates, and that physically changes the angular momentum. That is what I mean with kinetic moment, right? That's the physical change of the angular momentum caused by ma, right? That was the equation that we had. dg is mg. Sorry, this is now for g. In general, it would be, over here, right? dA is ma. Kinetic moment is the sum of all torques about sort of the same reference point. What is this? No, something absolutely non-physical, because it is simply accounting for the fact that your reference point, in this case, we allow the reference point to change. So if I have a particle here, and that's moving with a certain velocity this way, and that means it has a certain impulse in this direction. Now, the choice of my reference point A determines how much angular momentum this had. If my reference point is close, small angular momentum. If my reference point is further away, larger lever arm, larger angular momentum. Right? This is how moments work. The further you go away, the larger the angular momentum is. Right? So your choice of reference point, and we saw this at the very beginning of class where we went from reference point A to reference point B, right? I get a different value for the angular momentum. The physics behind it is the further I'm away, the larger the angular momentum. And I'm saying this is non-physical because whether I choose point A or point B is my choice and has nothing to do with this particle moving through space. So if that point A is now not stationary but has a velocity and is sort of slowly moving down, and I have my particle here moving with constant speed, it will seem as if the angular momentum increases because the lever arm increases because this point A is moving. This is the physical, or that's the meaning of what's happening back here, right? It's not something physical. Physics don't change, but the reference point that I chose happens to move. And if the reference points that I chose happens to move, then somehow lever arms change and the angular momentum that I compute gets larger. We normally don't want this. And so we will focus on two special cases. Number one, point A is an inertial point of reference. It's not moving. VA is 0. And the contribution from this disappears. This would be called that Drallsatz in technische Mechanik, where you simply assumed this reference point, to be stationary. What is the other option? I pick the other way around. I pick A to be G. I pick the center of gravity as my reference point. And then, of course, the velocity of this point A is going to be parallel to Vg. And that cross product here is also 0. This would be called the Spinsatz in our undergrad lectures on technische Mechanik. In those two special cases, this goes away. For arbitrary moving points, which I explicitly allow here, you would have to remember to carry this with you. And those are basically the equations that I get for rigid body motion. Kinetic moment about the center of gravity is equal to the sum of all torques about the center of gravity is equal to the physical time derivative of the angular momentum about the center of gravity. Spinnsatz. Kinetic moment about some inertial reference point, stationary, is equal to the sum of all torques about that stationary point is equal to the change in angular momentum about that stationary point. Drallsatz. And then we have the more general case, kinetic moment about a non-stationary point A is equal to the sum of all torques about this non-stationary torque A is equal to the change in angular momentum plus this cross product back here, which basically corrects for the fact that my angular momentum changes because the reference point is changing, which is non-physical, which doesn't require a torque, right? Even if there's no torque, but my reference point moves, right? If I have an object moving at constant speed, it has constant linear momentum. Physically, nothing changes, but if I move further away from this, the lever arm will change, and my angular momentum that I see about that point will change. And so this corrects for that. These are called the Newton-Euler equations for rigid bodies. And now I'm summarizing physics. Sum of all forces is equal to the change of total momentum, where total momentum is defined as mass times velocity of the center of gravity. Sum of all torques about the center of gravity is change of angular momentum about the center of gravity. And then this is just summarizes how we compute the location of the center of gravity, how we compute angular momentum, and how we compute this inertia matrix AG. And then here, as a reminder, right, this we will in everything we will do in this class, we will use G as our reference point. But if you ever choose others, it works the same for I. You need additional terms for A. Does the template say I here? I don't know if we updated our template. Just check. It may say G, which is wrong. Or what does it say? I. OK. Yeah, never mind. This has been fixed. My notes say typo in template. Now the note says, don't care about this. OK, I want to do an example. And you find this on your template. You have here a little system. Consists of two particles, which means my center of gravity is nicely smack here in the middle. Particle 1, particle 2. And I have a motion around the two axes. So in this example, my omega b is in this b coordinate system. Oh, sorry. Let's do this in I coordinates, just to be sure. In the coordinates that we have here is 0, omega 0. So rotation about the two axes with omega. And I first want to do this in 2 steps. I want to go through velocities, linear momentum, and then angular momentum. So what is the velocity of this particle over here in I coordinates? Who can tell me? Where's this particle moving to? So maybe to visualize, this is the situation. Momentarily planar. So I have two particles. Scale this, two particles. One here, one here. We're rotating about the two axes. What's the velocity of this guy? Into the plane, and the magnitude. So into the plane means 0, 0, and then something minus. And magnitude? omega x. Right? So I have to take omega times the distance from the rotation axis, omega x, into the plane. This guy here comes towards us, same magnitude. Right? So here we would have a velocity v2, which in I-coordinates is 0, 0, and then plus omega x. You have a question? Sorry.
No.
Is it my handwriting?
No, I started with my pens.
I have 3 that also don't work. If you if you want to trade. So those are the velocities. Now my angular momentum in I-coordinates is now the sum over all particles, and for each particle I take the cross product of the vector from my reference point, in this case g, to the particle, and I take the cross product with the linear momentum of each of these particles, which in the case of particle 1 was minus m/2 omega x. And then for the second particle, we would have the coordinates minus x, y, 0. And the velocity was 0, 0 plus omega x, which means that the linear momentum is m/2 omega x in the positive z direction here, right? Positive 3 direction. Then we evaluate these guys. I pull the m/2 out here, and in my first cross product, I get minus omega xy. I get plus omega x squared. I get 0. And in the second term, I get minus omega xy. I get plus omega x squared and 0. And if I sum this up, I would get, I see this is 2 times exactly the same. So I get m times omega. Can pull that out. And I have minus xy, x squared, 0. Did I screw this up?
Yeah, shouldn't there be minus y in the second yellow column?
Yes. Thank you. Otherwise, I will get a plus here, which I don't want. Let me draw this. Where's LG pointing to? Now I can draw this, right? This is a vector. Where's it pointing to? Who can tell me? There are your coordinates, minus xy, x squared, 0, and then scaled. I could also take the x out because we don't really have a notion of scale here. So I have minus y and plus x. So minus y in the x direction and plus x in the y direction, which means that this guy sits orthogonal to the connection between these two particles. So this is LG. And we clearly see that it is not orthogonal to our vector omega b. And I hope we see why, right? I have a rotation about this axis, but this basically means that point is going this way, this point is coming up that way. And we could generate the same effect by having a rotation about this axis as well. Right? So somewhere with these cross products and projections, we're losing information. That is LG, not parallel to omega b. Here I went sort of the way through going through the linear momentum and then multiplying with these lever arms, now in the sense of a cross product, to get LG. I could have done it the same way going through the inertia matrix. And the inertia matrix would be the sum over all particles. And then we have these row expressions where here, row 1 is plus or minus x, plus for particle 1, minus for particle 2. Row 2 is plus minus y, and row 3 in all cases is 0. So I would get for my inertia matrix sum over all particles, mass of the first particle, m over 2. And then I have row 2 square, which is going to give me y square. I have minus row 1, row 2, so minus xy. Then I have minus row 1, row 3, that's a 0, minus row 1, row 2, of course it's symmetrical, row 1 plus row 3 square, so we get x square here, we get another 0 here, we get another 0 here, another 0 here, and then here I get x square plus y square. This would be particle 1 when I set row 1 to x and row 2 to y. For particle 2, I would do the same thing, but set row 1 to minus x and row 2 to minus y. So here I would get minus y squared, which is the same as y squared. Here I would get minus x times minus y, which is the same as minus xy. Here I would get minus x squared, which is x squared. So we see it doesn't matter. The contribution for these two particles to our inertia matrix is the same. So I can simply add a times 2 back here. And with that, I can now compute my angular momentum. This is, of course, in I coordinates. In I coordinates equals m times, and now I have to multiply 0, omega 0 with this matrix. So I get minus xy, x squared, 0, and omega. Which, of course, is the same result. And in the background, this guy does exactly what we did here, right? It takes the angular velocity, somehow multiplies it with a bunch of lever arms, so that internally you get velocities. Then the velocities get scaled with the mass. And then those linear momentums are projected into an angular momentum. And this is what we have here. Some of you may be confused because I always talked about how great it is to do things in body fixed coordinates, and now here I did it in inertial coordinates. Still works, of course, right? The math doesn't change, but what would change is that if this thing now starts rotating, I would get a different inertia matrix, right? Just imagine I get a rotation about 180 degrees. Then that x turns into minus x, that minus x turns into plus x. So all of a sudden, these terms will change, right? Not on the diagonal, but here the signs will flip. And that is, of course, something that I wouldn't want to have in an algorithm where I want to specify this inertia matrix only once. I want to stop here, right? We haven't talked about how this moves. So there's your cliffhanger. Next Tuesday, we will deal with the question of how does it move, right? Will it keep rotating about this axis? What will it do? But Thursday, first exercise, homework, problem 6. And if you haven't done so, super important, install Git. And get Git running, and ideally do this today. Because if you have some trouble, you still need time to reach out to us, send an email to me or Iskander, and we help you set it up so you can get the examples, the templates, and you can do your homework. Thank you.